let's introduce acceleration. So as you jump from speed and velocity, and you kind of do some examples related to uniform velocity, so where the uniform velocity just means that it's not changing on us, so it's basically constant. Eventually, you're going to start studying acceleration, which is the concept that you have of possibly speeding up, slowing down, or maybe changing directions. Now, the changing of directions, maybe I will avoid it in this video because it's an introductory acceleration concept. So I just want to focus in on first just kind of one-dimensional movement, so speeding up or slowing down, and then relating it back to displacements that you have and also velocities, okay, that you're carrying through. So for speed and velocity, I'll put up a link up above there. You can certainly go over that concept if you haven't already. You should be familiar with that before jumping into acceleration. So acceleration is defined as the change of velocity over time. So these concepts of speeding up and slowing down indeed imply that we are changing our velocity. Now, the change of velocity that we're carrying through, if we wanted to be able to capture it, it is indeed a rate. So it's the rate of how our velocity is changing. And that concept is captured in this formula over here. So we have the fact that acceleration, number one, is a vector. So it does have a direction. And the sign also implies something for us with regards to the movement, and then the reference we take. The change in velocity that you have, so that's something with regards to your final velocity and your initial velocity that you have. So it's almost the same definition like a rate, where you were talking about velocity and it was the change in your positions, which basically meant the displacement that you carry out. So with this formula, what we should know is that the units themselves, you can relate back, and kind of see that if you're going to be talking about velocity, that means the velocity, at least the SI unit, so the standard unit that we have is meters per second. Of course, velocity can be in kilometers per hour or many other units, but if you want to work in the SI standard units, then you would have to change that. For your time, so this is divided by the time, so right here. So what you would have is that this is going to be in seconds, and that is actually the unit for acceleration. And you might say, okay, well, that's kind of weird. I don't like writing it this way. And indeed, most physicists, and science or math, anywhere that you see, you rarely will see it as meters per second, over second. Well, what you typically will see this written as meters per second squared, which is the simplified form if you just kind of look back and think of fractions and how to simplify this. And of course, that shouldn't shock you because you have a second over here and a second over here. So it becomes squared because there's two of those units. So that is what we typically will designate our unit for. You'll see it that it's going to be per second squared. But in reality, what it means is how your speed is changing every second, right? So either it's going up or it's coming down, at least for us at the moment, because we're referring to just speeding up and slowing down. So how would we apply this particular formula? So here's a little example to get us kick-started. So let's imagine, we have a cyclist, and this particular cyclist, is moving at 10 meters per second west. So that is the first initial, speed of the cyclist that we have. And then that cyclist is slowing down to 2.5 meters per second and still going west, so in the same direction, to avoid a major crash. So we would have our initial, velocity, so within here, so that is 10 meters per second west that we would have. Slow down, so our final one that we have is 2.5 meters per second, still west. And now this whole thing, it looks like it is taking place over a duration of 5.2 seconds over here. And we want to find out what the acceleration is, or at least what the cyclist experiences, and round it to two significant figures. okay, in here. I'll put up a link to significant figures over there in case you've forgotten. So with this, what I have, so the last component is the change in time over this whole process was 2.5 seconds. Now, always just double check. So notice all the units are actually aligning, right? So this is something that you typically take for granted, but just be careful. So stay consistent on your units if you want to be able to have the SI, okay, unit as your standard. So now our actual acceleration, so our acceleration, which is a vector, we are taking an average because we're taking it between two particular points in time, between your initial and then your final. So, you know, during that time, what's the average, okay, change in our acceleration? So that's what we're trying to do. And as a whole, in terms of defining this is the change, okay, over the change in t, which really is written out. So this is going to be v final minus your v initial. So these are two vectors divided by, and your change in time typically would be your t final minus t initial. But of course, if they give you the whole duration, then that can be replaced by that delta t, which is just the change in time. If you substitute all of this in here, and notice that, you know, I am going to keep these directions the same. So when you're substituting in, make sure that the actual direction is the same, right? So that you're easier, so you can just add the vectors or subtract the vectors as needed. And so for this, we're going to have 2.5. This is meters per second. I'll just drop it. And it's already west, so I'm going to just keep it, okay, on the outside there. This is going to be minus 10. This is all going west. And so in here, so this is going to be over the duration, which is 5.2 seconds. So everything lines up. So notice that it is 7.5, and it's going to be negative over 5.2, and this is going to be west in that case. And now if I substitute that in, so 7.5 divided by 5.2, which is 1.44, etc. They wanted us to round this, so I'm going to round it. So it's going to be 1.4. This is to 2 sig figs. And it's going to be meters per second squared west. All right. Now, if you are visualizing this for yourself, you know, so what does this mean? I like to kind of draw this out. So west is in this direction, right? So west is basically, well, to the left, at least by the standard convention. So this is, you know, going west. So that's how the cyclist is moving. So the cyclist is moving west. And accelerations, the way that they work is, so here, if you have your direction, so if you're assuming the direction is west on the acceleration, but this, okay, is negative, so that means it's on the opposite side. So really, if I was drawing this out, okay, then this would kind of look, okay, as it was going in this direction. So it is it's opposite of the actual movement, okay, that you have in there. So what this would tell us is that this is actually slowing down, right? So this is what's happening over here, that it is actually slowing down. That's what we have, okay, overall. So we're still moving, right? Because we're still going in the positive direction. So it's at 2.5, but it's forcing us to slow down. All right. So that's how we can calculate accelerations for these. That's not very difficult in terms of trying to utilize this particular formula. At least I hope that you can substitute things in and then carry out. The directions sometimes will throw us off. So this was an example really of slowing down, and then we had our standard units. So now, in general, okay, as you're kind of heading along, you may notice, and let me kind of steal, okay, this particular, so I'm going to just copy this, okay, in here. I'm going to bring it down, so I'm going to paste it back. So if that's our actual formula, you may recall that when we're studying velocity, we had these position time graphs, right? And these particular position time graphs we could draw out, and when we knew that the slope of the position time graph was actually, okay, the velocity itself, right? So we can figure out what those actual velocities were from the position time graph. Well, here, notice that slope was rise over run, right? Where we put position on the vertical, on the y-axis, and time on the x-axis, on the horizontal. Now, for acceleration, we can do the same, except we can just simply swap. So notice this is, okay, your velocity over time. So if we were trying to draw out, so instead of having a position time graph, like so, right, we could draw this out, okay, and put this in here. And now we can say, all right, so this is our time. We'll keep it in seconds. But here we can say, oh, this is our actual velocities, okay, that we have. And you know, maybe this is in meters per second, and let's, you know, keep it east, okay, as being positive, although you can keep it any direction you like. And now this from right here, this gives us the actual slope. And the slope over here that we would have, because slope is rise over run, if you are writing out and going through, instead of a position time graph, now a velocity time graph that we have, well, from here, what we can learn is that the actual slope itself is going to be giving us the acceleration that we have. So the same way as we did for the velocity and the position time graphs, we can say, okay, well, if, you know, this is flat, right, that means the slope is 0. So that means there is no rise, okay, it's just a run. You know, so what would this mean? This would tell us right here that, you know, we would be stuck at a constant, okay, velocity over here. So we would have a uniform velocity. So we're not really changing, right? At every single point right here, our velocity stays the same. So it looks like it's some positive value in the east direction. But because acceleration is the change of velocity, then that means in this instant, our acceleration would have just simply been 0, right? Because it's flat. So that's not shocking at all. Now, if we swap this, right, and then I put it over here on the negative side, well, what that means is, again, so now on the negative side, this means with respect to east being positive. So this would have just simply been telling us that our velocity is going to be, so it's still flat, right? So it's still constant, but it's negative, which just means that it's going west, right? So that's what it means, because it's on the negative side. So negative of the east would just simply means that it's west, but our acceleration is still flat, right? So nothing really changes over there. If you, on the other hand, okay, have a velocity, let's say it's positive, okay, like so, well, now all of a sudden we can say, oh, well, now we do have a slope, right? We do have a rise and we do have a run, right, as you're going through. And our rise, well, our rise is going to be just the change in velocity. So as you go from here to here, that's your rise, whatever those values are, right? So we could figure out what those values are. So that would have been our rise right there. And then our run, so, you know, from here to all the way over here. So that's the change in time, and that's right there. So the slope from the velocity time graph is actually our acceleration. And now this slope would have been positive, right? Because it's rising upwards. So when this is positive, what does that tell us, right? That our acceleration is positive. So this is telling us that, you know, as you're going along, it looks like, oh, my speed is increasing, okay? And I'm moving along in the east direction here, right? So that's from here. But it is actually increasing. So my speed is increasing. So it's, you know, it's speeding up. And because my acceleration is positive, right? So that's the speed up. So my acceleration would have been also positive in the east direction. So that's what would have been happening over here. Now, you know, I could, okay, change this around and I can say, oh, well, now my slope is going to be negative, like so, right? So now my slope is negative. My rise, on the other hand, is no longer a rise. It's basically a fall, right? So this is going to be a negative amount. This is going to be a positive amount on the time. And in this case, so your actual slope is going to be negative. Now, what does that mean for us? So here, notice we're started over here, and it looks like, oh, well, the actual velocity, so I'm still moving east, but it is slowing down, right? So I am still moving along, and I'm going in the east direction over here, but I'm going, you know, in terms of speed, I'm slowing down, okay? So notice that this is coming down right here. So my velocity is coming down, but I'm on the east side. So I am moving in this direction, right? But my slope is negative. So my movement is now, okay, notice my acceleration, okay, it would have been in the opposite direction. It would have had a negative, okay? So this would have been negative east, okay, that you would have. That would have been a slowing down. So that's something that you can think about. And of course, you know, we can move this over and we can bring it over on the other side, over here when it's on the negative side. And here you have to be careful because as you're moving along here, so notice that here you're started off right here. So this was a negative value, but it was a small negative value in magnitude. And now notice as time goes on, this is more negative, more negative, more negative, more negative, more negative. So what does that mean? Well, that means you're going west and you're actually speeding up here, right? So it's getting more negative as you're going along. So you're just going in the opposite direction and you're speeding up. You're basically moving along. The slope of this is negative, right? As you can see there. So it's the same thing. It was negative over here. It's negative over here. It doesn't change. The slope's still negative. But now you're moving in the other direction. So notice that you're moving in this direction, okay, and your acceleration is negative, so it's also in the other direction, so they're the same. And now, in this case, intuitively means that we are actually speeding up, except we're going west. All right? So that's something always to think about, right? Now, if you had your graph as you're going along and it was like this, well, in this case, notice that initially, right, so this would have been a very negative amount, and then, okay, it's less negative, less negative, less negative, and so on. So it looks like, now in this case, okay, the velocities are negative, but it looks like I am now moving, okay, in the opposite, okay, direction. So I'm going west, but I am actually, so I'm moving in the west direction, so I guess this way, but I am slowing down. My speed, my magnitude of the speed, okay, is decreasing. So now, in this particular case, notice that the acceleration, which is the slope, well, the slope is positive because this is going upwards, but it is in the opposite direction of the movement, right? So you are going, okay, in the west direction, right? The acceleration is in this direction, so they're in opposite ways. And it turns out whenever your motion and your accelerations are in the opposite ways, then you're slowing down. If they're in the same direction, so if your motion and your acceleration is in the same direction, then you're speeding up. So that is something worth keeping in mind. In terms of calculations, as we saw in the previous example, it doesn't seem like much, but the intuition of understanding acceleration is useful to be able to know, right? So those are the actual graphs, and you know, you can do these graphs and you can do all kinds of wonderful things. You know, you can have these graphs as you're going through, and then you can say, oh, you know, what's happening through all of these stages. But this is now your velocity time graph that you have. So in here, you know, you notice, oh, I am, you know, positive slope. This is a positive slope. I'm going in the same direction because it's on the east side. So it looks like I'm speeding up. Here, it's a slope of 0. So basically, I'm just maintaining my actual velocity here. So no acceleration at all. And then over here, it looks like I am slowing down, right? As I'm going through, my speed is, okay, decreasing, but I'm still moving in the east direction. Okay, so in this case, my acceleration would have been negative slope, okay, in the opposite direction, and I'm slowing down. So that is something, you know, worth thinking about. Now, I wanted to point this out to you before I close this video, because acceleration on its own, in terms of slopes from velocity time graphs, hopefully is not bad. The definition, okay, and the formula used is also not very heavy. It's rather simple to be able to use. But how would we relate this back? Okay, so this was, you know, velocity time graph that we have. But how would we relate it back to a position time graph? Right? So in a position time graph, when we were talking about, we never had any curves. So when you study position time graphs just for velocity, for uniform velocity, right? So you have a nice straight line. So you would have things like this. You would say, oh, well, you know, maybe it's like this. What does this mean, right? So in terms of flat line, okay, well, in a position time graph, that just means that you're stuck in the same position. You're not moving anywhere and time just continues to go on. So that means there was no velocity, right? It was zero. So that's fine. Now, we've also ran in, and you've kind of ran into the situation where maybe, you know, you had a straight line. And that was fine. So it looked like your position, you know, you were moving along, you were getting further and further, in this case, east, right, as you keep moving along. But the slope was constant in here. And again, don't forget that in a position time graph, the slope means it's the velocity, right? So the velocity was constant. It had the same slope all the way throughout. Now in these graphs that I have just drawn, well, these are not straight lines. These are curved lines. So how can we think about these particular curved lines and then what is actually happening to them? So that is interesting. So in here, as you're going along, at any point, right, it looks like your position is changing, right? Your position is, you know, you're moving upwards, okay? So you're moving away, you're going east somewhere as you're going through. But the graph itself is not a straight line. So you're not moving actually no longer at a constant velocity. Your velocity is changing, and that means you're accelerating. Now, how can we tell this? Well, a very nice little trick for yourself is that you can tell that from slopes, we know that the slope from a position time graph relates it back to velocity. So here, you know, I've constructed for you, so this is kind of a simulation that you have, and you can see that I can take the slope and put it as a tangent to that curve, right? So imagine this is your position, this is your time in terms of your axes. It's not a straight line, but I can put a tangent at every single point. And understanding a tangent, okay, is okay, well, I can write a straight line and just kind of attach it. And that is the slope at that point. So it's the slope of a line to that point. And notice it's very flat over here, but then it starts to curve upwards. So whenever you experience this in a position time graph, where your actual slope changes of the tangent, that means that there is acceleration. And notice that the slope means it's the velocity. It's actually the instantaneous velocity. So it's the speed at a particular point in time, right? As you're kind of driving in a car, you'll look at the speedometer and you'll be like, oh, you know, what am I going at right now? That's the speed, right? That's the instantaneous velocity. That's not the average velocity, right? Where you're taking an average over a long period of time, maybe sometimes a short period of time. And if you do notice that it is increasing like this, that the slope is getting steeper and steeper, well, what does that mean in relationship to the acceleration? If your slope right, is positive, okay, that you have in there, well, what did we say about that? That means, okay, that your acceleration in this case is positive. Now you're moving, as you can see there, so if the vertical is the east direction, so this would have been the movement in the east direction over here. So your acceleration, so it looks like you're speeding up. So that's what you would have in there. And the same thing can happen in all the other curves, right? So on this first one, okay, so that this one that we would have, if you were relating it back, this would have been, you know, positive acceleration because your velocities, you know, keep increasing as you have there. Now, the one on the right-hand side, so this one right here, you can see there that, oh, well, the tangent, right? So as you're going through, right? So first it's very steep, then it's less steep, then it's less steep, and then it almost becomes flat. So that is the instantaneous velocity. So that instantaneous velocity as you're going along there, so it looks like it's becoming less and less positive, right? So that would have been, and if you would have been graphing this on the velocity time graph, so it's, you know, very large, so very big, and then it's getting less steep, so basically your velocity time graph would have been going downwards. That's what you would have had. And that means, okay, so in that particular case, it would have been a negative acceleration in there. So this would have been a negative acceleration. And again, so over here, as you're going through, so now you have to be careful and see kind of what happens. So for this one, okay, so this one is going, it looks like it's flat, okay, then it looks like it's a little bit steeper but negative, steeper but negative, and steeper by negative. So it's getting more and more negative. So if you were looking at this, you know, you would have had, okay, so in here, it still kind of looks like it would have been, okay, a negative kind of, you know, your actual velocity, right, as you're going through, it was from flat, and then it goes more and more and more negative as you're going along. So in that particular case, as it's becoming kind of more and more negative, then your acceleration, okay, is, so it looks like it is, now it's going in the opposite direction, so it's not going east, it looks like it's going west, right? So your position, so you're going west, okay, and your acceleration is also negative. So you're moving in that motion, so it's still speeding up, but here your acceleration is negative that you have. In the last diagram that you carry through, so in here, in this one, so notice that it's very steep, okay, and then it's less steep, okay, and then it's less steep, and then it's less steep, and then less steep, right, as you're going through. But notice that in this direction, okay, as you're going through there, so as it's going in this direction, so this was, you know, negative, negative, okay, as you're going through, negative, and then negative over here, okay, in terms of your actual, but it's going less negative, right? So it's very, very negative. So if you were thinking back, okay, and you were thinking about your velocity, so if you would draw out your graph, so right here, so this is what you would draw. So let's say this is your velocity, okay, going on the east side, this is your time. Notice that your slope over here, so it's very negative, right? So this is very steep, so it would have been somewhere over here. But as you're going along, you know, so this one is, it's still negative, okay, but it's less negative. So it would have been somewhere over here, okay, as you're going through, okay, and then again, here it's almost flat, so it's getting even less negative. So here it's kind of going in there, so you'd have had something like this. And notice that this is not the greatest of drawings in here, but from very negative to less negative as time continues, this looks like it's a positive, right, slope, so positive acceleration that you have, but you're going in the opposite direction. So here you would have been actually slowing down. That's what you would have seen in this, from this particular diagram. So in terms of acceleration, Okay, this is some of the things that you're going to be running into, and hopefully, okay, as you touch on these concepts, okay, it's going to become more and more understandable in terms of speeding up and slowing down. All right, thanks for watching. We'll see you in a future video. Bye, everybody.